Lawyers are often quite stubborn. They continue to fight for the cause of their clients, even though they should know that they can never win. Well, that is how they earn their money. An engineer, however, should act differently. He or she should develop the intuition of how to recognize lost causes and the courage to abandon them. Which does not mean cry over spilt milk or throw in the towel. No, it just means looking for more realistic solutions for a given task. I should like to present 3 issues from the world of engineering which I consider, at least partly, as lost causes. First, wireless power transmission as Tesla envisioned about 120 years ago. Second, superconductivity at normal temperature and normal pressure. And third, harnessing useful energy from nuclear fusion on Earth. Let's start. Let us look back to the origins of electrification. At that time there were 2 combating inventors. First, Thomas Alva Edison, who pushed a direct current power system with his own company. Second, Nikola Tesla, who worked for the enterprise of Westinghouse and pushed the use of alternating current. As we know, alternating current systems won in the end, mainly because AC can easily be transformed to different voltages. However, Tesla's vision was a wireless transmission rather than a transmission through buried cables or overhead power lines. Tesla wanted to achieve such wireless transmission by means of such towers, using his Tesla coil to create high-frequency waves. He got the money to build this tower, pretending that it was used for information transmission rather than power transmission. When the investor knew the truth, he stopped the project. Concerning information or power transmission, I'm coming back to that later. But let's see if such a system could work at all. The problem is, electromagnetic radiation can never be perfectly focused. So the power will sort of thin out over the distance. A bit more scientifically expressed, the power density will decrease over the distance and does so inversely proportional to the square of the distance. We could think of using an isotropic antenna as a transmitter, that is a hypothetical antenna that emits the radiation, ideally distributed in all directions. If our receiver then covers an area of 1 square meter, we will even in a modest distance of 1 kilometer only be able to collect 80 billionth of the emitted power. Forget it. So, let's assume that we are using a beam antenna with a directivity of 10 to the power of 7. That means it focuses the radiation 10 power to 7 times more than an isotropic antenna, which per definition has a directivity of 1. This is about the best directivity a microwave beam antenna can have. Our 1 square meter receiver then collects 80% of the emitted power in a distance of 1 kilometer. Okay, now this sounds reasonable. But over longer distances, the beam antenna will fail as well. Okay, let's try a laser beam. Lasers can be focused to such an extent that a beam sent from the Earth can produce a light spot on the Moon with a diameter of no more than about 1 kilometer. Since the distance from the Earth to the Moon is about 380,000 kilometers, the diameter of the beam will remain well below 1 meter at distances up to some 100 kilometers. So, if we neglect the weakening of the beam in the atmosphere, our 1 square meter receiver could collect all the power over such distance. This might work theoretically. So, our assessment of technologies in a nutshell. Forget microwaves emitted by an isotropic antenna. Microwaves emitted by a beam antenna might work up to about 1 kilometer. A highly focused laser beam might work over distances of 100 km and more. However, lasers did not yet exist in those days. But would we really want it to work? We are doing anything to prevent people from touching a high voltage power line. But we would also need to prevent them from getting in the way of a highly focused high power beam. Where is the advantage of wireless transmission compared to cables and overhead power lines? Tesla seemed to be completely aware of the dangers, but in his later years he even welcomed such power beams for use as a weapon, as shows a newspaper headline of those days. But don't let us stay with these martial aspects. In fact, Tesla's proposal was the perfect solution, but for a totally different task. Not for wireless transmission of power, but rather for wireless transmission of information. Because for this purpose the incoming power density is of minor significance. As long as we still can detect the signal, everything is okay. Tesla could have joined others who already dealt with the use of electromagnetic waves for information transmission, but he remained stuck in his own world. I'm really convinced that wireless power transmission over longer distances remains a lost cause. The history of superconductivity began as early as 1911 when the Dutch physicist Heike Kamerlingh-Onnes experimented with liquid helium. Thereby he discovered that the electrical resistance of solid mercury abruptly dropped to zero when it was cooled to a temperature below 4.2 Kelvin. Wait a minute. How can we see that the resistance is exactly zero? If we are placing a magnet over a superconductor, this action will induce a circular current within the superconducting material. This current in turn creates a magnetic field which repulses the magnet, making it hover over the superconductor. The thing is, since the resistance is in fact zero, the current will not subside and the magnet will not drop as long as the state of superconductivity lasts. Which means as long as the temperature stays below the critical temperature of the superconductor. Of course, a material without any electrical resistance awakens dreams of lossless power transmission. Unfortunately, the first superconducting materials all required a very effortful cooling by liquid helium or liquid hydrogen. But the development went on. Let's follow it using a temperature-pressure diagram. We shall see in a few moments why pressure is essential too. In the year 1930, niobium was found to become superconducting at a temperature of 9.2 Kelvin. Niobium was followed by niobium germanium, Nb3Ge, with a critical temperature of 23 Kelvin. Now, this led to the first technical applications. By means of superconducting coils, it was possible to generate strong magnetic fields as they are used in medicine for MRI scans of the human body. Even first superconducting cables were produced, but only for short distances. In the second half of the 1980s, development took a further leap. The first so-called high-temperature superconductor was discovered. But you can't be serious. You are calling a temperature just above the boiling point of nitrogen a high temperature? Well, yes. For an engineer, minus 196 degrees Celsius might be cold, but for a physicist, 77 Kelvin are really warm. But all jokes aside, more superconductors of this sort were found, but one was, of course, still far away from standard temperature superconductors. At that, the new materials were, and still are, brittle, thus difficult in production and processing, partly consisting of rare or toxic components, in short, not what you always wanted. Nevertheless, new applications opened up, above all, superconductive cables over reasonable distances. In the year 2020, the world was shaken up by the news of having found a standard temperature superconductor. Wow, a dream come true? Unfortunately not. Now we see why I introduced pressure into the diagram. A material that is superconductive at a temperature up to plus 15 degrees Celsius, it's true, but only at a pressure of several hundred gigapascal, more than 1,000,000 times the standard air pressure on Earth, far more than the pressure needed to transform carbon into diamonds. A rude awakening after a beautiful dream. As if nature wanted to tell us, do not dare to come anywhere near the point of standard temperature and pressure with your superconductivity. It seems that superconductivity is a highly unnatural state, occurring only at conditions far away from nature, and thus very hard to achieve artificially, requiring either a very low temperature or else a very high pressure. But you do have to achieve at least one of these. Okay, anyway, even so, superconductors are very useful for many applications. But I'm quite sure trying to find a material that is superconductive at standard temperature and pressure will remain a lost cause. The fact that energy can be released as a result of nuclear processes has its origin in the different nuclear binding energies of the elements. This graph shows the binding energy per nucleon for some elements, which means the total binding energy of one atomic nucleus divided by its number of protons and neutrons. Since, for example, the normal hydrogen nucleus only consists of one nucleon, a proton, no binding energy is involved at all, so its value is 0. The binding energy per nucleon reaches a maximum for medium-sized elements such as iron. Since I oriented the ordinate of the diagram downwards, this will be the lowest point of the graph. These elements are the most stable ones. Heavier elements have lower binding energy per nucleon. They become ever less stable. Now, whenever an atomic core is transmuted by some nuclear process into a core with higher binding energy, the energy difference is set free. That is important to understand. The transmutation of atomic nuclei towards higher binding energy does not require energy. The opposite is true, it releases energy. That's the reason why I oriented the axis downwards. You can imagine that the original element sort of falls down in the energy valley, thus releasing energy similar to the potential energy of a stone falling down a slope. There are a number of different nuclear processes leading to such a release of energy. One of them is the natural decay of elements. There are some processes which take place to a considerable amount in the Earth's crust. On the left side of the graph, shown in green, the decay of potassium into the inert gas argon as a final stage. Or on the right side, three processes that are nearly undistinguishable in the diagram: the decay of thorium and two different uranium isotopes into different lead isotopes as the stable end products. These natural processes are the main source of geothermal heat, one of our renewable energy resources. Another possibility to release nuclear energy is to split heavy atomic cores into smaller ones. This is what we call nuclear fission. It is the process used in today's nuclear power plants. It is based on the fact that the core of the uranium isotope 235, the one which has a total of 235 protons and neutrons in its core, splits in two smaller cores when it is hit by a free neutron having the appropriate speed. The diagram shows one possible example. The products of the split need not always be the same elements. On top of the two smaller elements, 2 or 3 neutrons are released. Splitting heavy nuclei is not too difficult. It happens even spontaneously in nature. As we saw in the diagram, 2 or 3 neutrons are released with each split. Each of them has the potential to split another uranium nucleus and thus initiate a chain reaction. When, on average, just one of the released neutrons splits one uranium nucleus, the reaction is in a dynamic equilibrium. If less than one neutron does its job, the reaction will eventually stop. If, however, more than one of the released neutrons performs another split, and this continuously, we become witnesses of a reactor catastrophe. Even such chain reactions can occur spontaneously in nature, though rarely. In the 1970s, one discovered anomalies in the isotopic composition of an uranium ore deposit in Gabon, Africa, which could only be explained by a nuclear chain reaction taking place about 1.7 billion years ago. As we see, the fission process can quite easily be launched, but then it can just as easily run out of control. That's exactly what happened 1986 in Chernobyl, then part of the Soviet Union, now Ukraine, and 2011 in Fukushima, Japan. One nuclear disaster every 25 years? That is too much, I think. But now, what about nuclear fusion? Fusion is the third process in addition to decay and fission by which nuclear binding energy can be released. To explore that, let us have a look at only the left side of our diagram, where we find iron and the even smaller nuclei. If we start, for example, with normal hydrogen, we can assemble several cores to form heavier ones. Helium, carbon, oxygen, silicon, to mention just a few elements. We shall see in a moment why these are particularly important. Sometimes we must add some neutrons to get the correct composition of the new cores. This does not affect the basic principle. The step-by-step process stops when we have reached iron and thus the highest occurring binding energy per nucleon. Now, it turns out that fusion can by no means be as easily achieved as fission. Why should that be? Because of the protons, each nucleus carries a positive electric charge. This causes a strong repulsing force between the nuclei, which must first be overcome before fusion can take place. This means a huge investment of energy before we can even think of harnessing energy. Stars are in no hurry and don't suffer from lack of space. Thus, they are able to gain a lot of gravitational energy while contracting out of thin interstellar gas. Using this energy to build up extremely high temperature and pressure, they can eventually ignite the nuclear fusion process. But only if they have sufficient mass. Then they can follow the step-by-step fusion process towards ever heavier nuclei, from hydrogen to helium. That is the current stage of our Sun. Later stages of star development involve carbon, oxygen, silicon and, eventually, iron. I mentioned that a star must have sufficient mass, otherwise it would not be able to gain enough gravitational energy to ignite the fusion process. Astrophysics says that about 6,000 times the mass of the Earth is the minimal mass below which a fusion process will not start. So the universe cannot produce a small-scale sun. Can we? With the help of physicists, some colleagues of mine try. And they can even present valid reasons for doing so. Hydrogen, which is meant to be sort of the fuel for the fusion process, is available on the Earth to a nearly unlimited extent. A fusion process involves no chain reaction that can get out of control. If something is going wrong, the process will intrinsically stop. As a matter of fact, it turned out that a small-scale fusion process can be achieved, but up to now only for a fraction of a second, and instead of using normal hydrogen, two special hydrogen isotopes must be used: deuterium, the isotope possessing a neutron in addition to the proton in its core, and tritium with two neutrons besides the proton. Deuterium is very rare, tritium very, very, very rare. And to establish the conditions under which nuclear fusion can take place, a lot of energy must be invested. Recently, one seems to have reached a point where, for the above-mentioned time span, more energy can be harnessed than must be invested to maintain the necessary temperature, pressure and so on. But considering all the machinery around, what we call the balance of system, one is light years away from a positive energy payback. For the sake of completeness, here the diagram of what happens in today's experimental fusion reactors involving the fusion of one deuterium and one tritium nucleus to a helium core. I must admit, with a mixture of respect for my colleagues but also some sarcasm, that there was some progress since research has started shortly after the Second World War. But I really do think that getting useful energy out from a fusion process on Earth will remain a lost cause. But there is good news. We already have a working fusion power plant. Its name is Sun. The real Sun provides enough energy. We don't need small-scale suns on Earth.